Hi, we have been looking at various data discretization techniques. Today we are going to look at another one called a Fisher-Jenks algorithm or natural binning algorithm. It also goes by a couple of different names you can see here. Okay, so it works somewhat similar to the k-means clustering we have seen, but internally it tries to reduce the variance within the group and tries to increase or tries to maximize the variance between the groups. Okay, so let's generate some data to test this algorithm. So again, here we are generating the data from three distributions. So this time we are using uniform distribution as well. In previous video, we saw all three normal distributions. Okay, so here we have a uniform distribution between 90 to 110 in the middle. And also for the third normal distribution, we have more data points. We have 2000 data points here, right? So this is our raw data. And this is the visualization. So the first one, it's a mean of 50 and standard deviation 10. This is a normal one. And this is a uniform distribution. As you can see, this is more tighter and the values are spread uniformly from the lower to the upper bound, right? Unlike in a Gaussian distribution where 70% of the values are within this one standard deviation, right? Here we have the equal spread. And the final one, here we have more data points, double the data points, also higher standard deviation 20 with a mean of 170. Okay, now again, similar to the k-means algorithm, we have to decide how many groups we want to divide into. Now for a real world data set, they are not this clearly separable, so we might do some experimentation to find out the optimal value for the number of groups. So we call this algorithm Jenks-Pi algorithm with the raw features and the number of groups we want to divide into. Okay, so it returns these breakpoints or the boundaries. So the first group is going to be between the lowest value, maybe 15 to 75, and the second group going to be between 75 to 137 ish, and like that. Okay, and then we are going to use these boundaries to assign label to each data point using the pandas cut function. So to the pandas cut function, we are supplying the raw data and we are providing these breakpoints. Okay, and the labels we want to give. So we are going to give the labels as group 1, 2, and 3. Okay, so this raw data, first we have divided into different groups using the breakpoints and Jenks-Pi algorithm, and then we assign the labels. Okay, all right. This is how the binning looks like. So here we have again the histogram of our raw data, and these are the boundaries for each group. So the first group lies between these two red vertical lines are the values, and the second one and the third one. Now if we look at the number of data points in each group, so the group 3, it has some close to 2000, maybe 1900 data points, right? So some of the values from group 3, those are assigned to group 2, so it's not exactly 2000. So some of the values from here from group 3 are assigned to group 2. So that's why we are seeing more number of data points in group 2, more than 1000. Okay, probably some 100 points extra, whereas group 1, which is clearly separable from group 1 and 2, it has the exact number of points we have when we constructed the data, right? So this one. So as you can see here, the group 1, it's a normal distribution spread from here to here. So the group 1, it has the exact number of data points as we generated, whereas some of the data points from group 3 has been distributed to group 2, that we can see from the below plot as well. Okay, all right. So this is again, we are looking at the raw data points, these 4000 data points along with their bin boundaries. So the first one, first group, it's clearly separated. Only just 1 point from group 1 went to group 2, but that's clear. I mean, uh, uh, this is more closer to group 2 compared to group 1, right? Whereas a number of data points from group 3, because it has this higher standard deviation, so all these data points are assigned to group 2. Okay, that's it for today. Thank you very much.